Hi class, hope that you are doing well. Today we are going to talk about the soil model and its basic physical properties. Here we go. To provide the basic characteristics of soil, it is necessary to define the proportion of each component and to be able to build relationships between them in numerical terms. Soils can be either two-phase or three-phase composition, and soil particles form voids that can be occupied with water and or air. In a partially saturated soil, there are three phases. That is, the solid soil particles pour water and pour air. A fully saturated soil is two-phase configuration including soil particles and pore water. In a completely dry soil, there are two phases as well, namely the solid particles and pore air. In a typical soil, the solid, water, and air are naturally intermixed so that relative amounts are difficult to envision. It is then suitable to detail soil's physical model where all components, while still available in their correct proportions, are split into distinct amounts. On the left-hand side here, you see an actual soil sample. In the middle, a sketch showing the quantities of soil mass, namely air, soil solids, and water. On the right-hand side, a soil physical model where all the quantities are clearly defined. Several models can be adopted, but the unit soil volume is the best among others because it is based on 1 cubic meter of soil solids and all other quantities are referred to it. The soil model can be utilized to define several important quantities with respect to volume and mass. Void ratio is defined as the ratio of the volume of void to the volume of solids and shows the amount of voids in soil mass. Soil consists of lots of void, which makes it rather porous and soft in regards to rocks. Soil with higher void ratios will probably give rise to more problems during construction as it may experience larger settlements. In general, the void ratio of sand ranges from 0.6 to 1. As for clays, it is typically higher, varying from 0.8 to 2.2. For organic soils, the void ratio can be as high as 5. For engineering aims, it is always preferable to deal with soil that has relatively low values of void ratio. Porosity is the ratio of the volume of voids to the total volume of soil. It refers to the voids of soil as well, but it is more prevailing for a rock soil type. The voids of soil mass is either filled with air or water or both. The degree of saturation points out how much water is available in the voids. It is therefore defined as the ratio between the volume of water and the volume of void. Soil whose voids are full of water is named as saturated soil, and its degree of saturation is equal to unity, or 100%. For dry soil, the void is filled with air, and therefore the degree of saturation is zero. It is a misconception that the soil below the phreatic surface is saturated. In fact, soil below the phreatic surface may not be fully saturated, since there is always some air trapped in the soil mass. If the soil is not fully saturated, let's say the degree of saturation is 63%, what shall we call it then? It is called unsaturated soil, whose behavior is more complicated and less studied than that of saturated soils. It has been displayed that suction can generate in unsaturated soils because of the capillary forces, and it can give additional strength to soil. However, in many design calls, the fact of suction is usually ignored, and the design is performed for saturated soil, which is considered to be the worst case scenario. Density is the ratio of the mass of soil sample to its volume. If soil includes water, its total mass will contain the mass of solid particles and the mass of water. It is also important to note that different terms such as bulk, total, wet, or moist density are used in the literature to refer to soil density. On the other hand, dry density is the ratio of the mass of solids to the soil volume. The question is, are the dry density and density of solids the same thing? No, they are not. The density of solids is the mass of dry soil divided by the volume of solids. On the other hand, the dry density is the ratio between the mass of solids and the total volume of soil. The difference, as you notice, is in the volumes used. While the volume of solids is smaller than the total volume of soil, the density of solids is always greater than the dry density of soil. As the density of solids is generally between 2.6 and 2.8 gram per cubic centimeter, the dry density of soil ranges from 1.1 to 1.8 gram per cubic centimeter, depending on soil condition. Water content, in other words, moisture content, points out the amount of water in soil, which is the ratio of the mass of water to the mass of solids. For saturated fine-grained soils, the water content can go beyond 100%. For example, very plastic soils that involve clay minerals such as smectite or montmorillonite, it can have more than 70%. High water content is another sign that soil may be loose and weak, and that special attention needs to be given to the soil. Can all soils have water content more than 100%? Or is it only possible for plastic soils? Very high water content is common for high plasticity soils that include smectite or montmorillonite minerals. as mentioned before. The clay particles of such clays are extremely small, forming very loose structure with lots of voids. Additionally, owing to the specific structure of these clay minerals, a negative charge exists on their sides that can attract and hold water. Compared to silt and clay, gravel and sand have relatively larger solid particles, and they do not have this ability to attract and hold water. For this reason, coarse-grained soils usually have water content around 30 or 40% when saturated. It should be borne in mind that organic soils can also have very high water content. The specific gravity of solids is defined as the ratio between the mass of a given soil and the mass of the same volume of water. It shows how heavy the soil particles are compared to water. The specific gravity is a dimensionless number, which typically ranges from 2.6 to 2.8. As many soils involve a significant amount of quartz, their specific gravity would be close to its specific gravity, which is about 2.7. For fine-grained soils, a special glass jar of about 50 milliliter, and for coarse-grained soils, a 500 milliliter or a 1000 milliliter capacity of glass jar are used. Now, initially, the empty, clean and dried glass jar is weighed, and then a certain amount of dried soil is placed in the glass jar and weighed together. The glass jar is filled with the air water and shaken to remove any air bubbles entrapped, and carefully topped up with water and weighed again. Finally, the glass jar is emptied and cleaned, and then filled with the air water and weighed again. Let us remember once more the definition for the specific gravity, which is the ratio between the mass of soil and the mass of water displaced by soil. We can also express G as in terms of masses measured, as formulated here. Air content is the ratio of the air void volume to the total volume of soil. There are several more frequently used equations associated with dry density, unit weight, saturated unit weight, and degree of saturation, which are obtained from the soil physical model. Let us see what the soil physical model is. For a given soil, show that the saturated density of soil is equal to this equation. As a first step, we need to draw the soil physical model based on what is needed. Since the saturated density of soil is required, the soil physical model must be two-phased system, namely soil solids and water. The model, as stated before, is built based on a cubic meter of soil solids, and the other quantities are referred to it. As shown in the figure, soil solids has a cubic meter of volume, and the other quantities are defined accordingly. Now, remember the void ratio. It is the ratio between void volume and the volume of solids. Since the volume of solids is unity, then the void of volume, which is occupied with water, is equal to void ratio. So the total volume is equal 1 plus E, which is also known as specific volume. Now, the soil physical model can be expressed in terms of masses as well. Since the volume of solids is equal to unity, the mass of solids is equal to density of solids. And the density of water is the mass of water divided by volume of water. Since the volume of water is equal to void ratio, then the mass of water is equal to void ratio times the density of water. Now, let us remember the basic definition for density, especially for saturated density. It is the total mass divided by total volume as shown in equation 1. Now then, if we put the related definitions in their places as illustrated in equation 2, we rearrange the saturated density in terms of void ratio, densities of water and soil solids, water volume, and the volume of solids. But in the equation required, there is GS parameter. For this, we need to remember the definition for GS, which is the specific gravity. Now, the specific gravity can be expressed in terms of density of soil solids and density of water. If we incorporate this definition into equation 2, we get equation 4. If the equation 4 is rearranged, we get equation 5, which is required. In general, when we deal with earthwork problems, we have to know the mass per unit volume of soil excluding water. This mass is referred to as the dry density. Therefore, show that the dry density of soil is equal to this equation. As a first step, we need to remember the wet soil density, which is the ratio between the total mass divided by total volume. The mass, based on our soil physical model, as shown here, includes mass of solids plus mass of water. We ignore mass of air since it is nearly zero. Now, this density can also be expressed in terms of mass of solids, moisture content, and the total volume as shown in equation 2. Since The dry density is the ratio between the mass of solids divided by volume. Equation 2 can be rewritten as equation 3, which is required one. Steps for the development of any similar equations dependent on soil physical models are like that. Remember the basic definitions such as void ratio, porosity, water content, specific gravity, and degree of saturation. Draw a 2 or 3-phased physical model based on what is needed. Assume either the volume of solids or the total volume is equal to unity if not given. And usually make use of the expressions given here. The unit weight of soil is defined as the ratio between the soil weight and its volume. The unit weight can also be related to soil density as shown, in which g is the gravitational acceleration, which is about 9.81 meter per square second. Similar to soil density, the unit weight can be referred to as bulk unit weight, moist unit weight, or dry unit weight based on the existence of water in soil. The common range of unit weight for soils is in between 14 and 22 kilonewton per cubic meter, depending on soil structures and water content. The question is, why do we need to know the unit weight? Isn't just the soil density enough? Well, in soil mechanics, the unit weight of soil is employed to calculate stresses acting in soil mass, and therefore the unit weight is more commonly used than soil density. Relative density is an important parameter for the definition of the state of cohesionless soils. When we procure a soil sample during field investigation, we measure its in situ void ratio. If this sample is compacted to its densest state, its void will decrease and the void ratio will reach its minimum value. It is also likely to attain the loosest state for the soil in the laboratory so that its void ratio will reach its maximum value. The relative density is used to compare the in situ state of soil with its loosest and densest state by a relationship. Here you are, the relative density is given in terms of void ratios explained just before. When soil has a value of the relative density, it can be classified as very loose or very dense, as shown in the table here. Loose soils would typically have loose structures and can be more susceptible to failure under loading. Relative density is usually employed for coarse-grained material to evaluate its liquefaction potential. The relative density appears to be mostly utilized for sand. What about clay? For clay, plasticity has a dominant effect on soil characteristics, and thus it is typically utilized as an indicator of soil resistance to liquefaction. The steps for the determination of void ratio of cohesionless soils are as follows. The minimum void ratio is determined by placing a standard compaction mold underwater. The soil is then placed in the mold in about 3 equal layers, each of which is compacted using a vibrating hammer. The color of the mold is then dismantled, the surface is leveled, and the total mass of mold, soil, and water is ascertained. From the quantities measured, we can simply calculate the saturated density of soil using this simple expression, in which V is the volume of mold. The minimum void ratio can then be obtained using this equation, the derivation of which was illustrated before. The maximum void ratio is determined by putting the mold under water and quickly pouring the soil into it from just about the top. The color of the mold is then dismantled, the surface is smoothly leveled, and the total mass of mold, soil, and water is determined. Similarly, the value of maximum void ratio can then be obtained using the following equations given here. Here it is, a practical example to show you how the soil physical model can be used in practical applications. Soil excavated from a borrow pit will be used to construct a road embankment. The figure at the top shows the borrow pit area, and the figure at the bottom shows the road embankment area. The soil obtained from the borrow pit has a specific gravity of 2.7, unit weight of 17.8 kilonewton per cubic meter, and a water content of about 21%. The soil at the embankment is required to be compacted to a void ratio of 0.71. If the completed volume of the embankment is 70,000 cubic meter, what would be the volume of the soil excavated from the borrow pit? It sounds a little bit tricky, doesn't it? There are several ways of solving this problem, but I will present you a very simple one. As stated earlier, as a first step, we need to draw soil physical models for both conditions, one for borrow pit and the other for embankment. Since the soils are not fully saturated or not fully dried, they are three-phased system. Namely, they contain air, water, and solids, as shown in the figures here. Our soil physical model is based on 1 cubic meter of soil, and all other relevant quantities are referred to it. So they are clearly defined on the physical models. It can be stated that the ratio between the volume of soil from borrow pit and the volume of soil at embankment can also be written in terms of specific volumes as given here. Now, what we know in this equation, we know the compacted volume of soil at embankment, void ratio of soil at embankment, because soil compacted at embankment at a ratio of 0.71. What we don't know is the void ratio of soil from barrow pit. If we determine E sub B, then we can simply calculate the volume of soil to be taken from barrow pit. To find out E sub B, the following calculations should be carried out. Since we know the unit weight and the water content of soil from barrow pit, we can simply calculate the dry unit weight using this equation given here. The void ratio of soil from the barrow pit can be obtained from another dry density equation expressed in terms of specific gravity of soil, unit weight of water, and the void ratio of soil. Now, if we involve the dry density value into this equation, we can get E sub B, which is the void ratio of soil from barrow pit. If we involve this value into this equation given here, it will result in the volume of soil needed to be taken from the barrow pit. It is about 84,210 cubic meter. Got it? Okie dokie. Now it is time to take a quiz. The first question, which of the following ratios are not related to volume? Yes, it is B. Good for you. The second question, the ratio between the volume of voids and the total volume of soil is named as no, I'm sorry, it is not. It is not. The answer is porosity, because we are talking about the ratio between volume of voids and the total volume of soil. The third question, which of the following statements is incorrect? Watch out, please. No, it is not. It has to be B. The void ratio of sand is generally greater than the void ratio of clay. Here you have the fourth question. The density of solids is the ratio between. Yes, you're right, but speak loudly, please. The answer is D. It is the ratio between the mass of dry soil and the volume of solids. Great job. Now the fifth question, degree of saturation is the ratio between the volume of water and what? It's easy one. Yes, it is C, active clay. Well done. The sixth question, the average value of specific gravity of clay would be around, you must be joking. No, it's not. Yeah, it is B, 2.7. Congratulations. You have another question. What would be the typical value of unit weight of soil in terms of kilonewton per cubic meter? Yes, you got it. It is B. Good job. The next question. Water content is the weight of water divided by... No, you must be kidding. Be careful. No, sorry. It has to be the weight of solids. Final question. The void ratio of organic soil can be as high as 5. Is it true or false? Easy peasy. Yes, yes. Congratulations. It is true. That's the end of lecture today, folks. Thank you for your participating and wish you a very wonderful weekend.